Okay, moving on to day 5. Hopefully you guys found yesterday's review to be helpful. All right, and because we're moving on to something a little bit different today. So hopefully you guys have day 1 through 4 kind of, you're settling down with that and you feel confident in it. Okay, because what today is a whole bunch of new facts and theorems, so we can put it in the statements and reasons column of proofs when we start those up again tomorrow. Okay, so just a quick recap, what a chord and what a diameter is. A chord, again, is a segment where the endpoints are on the circle, so that's my pink segment right there. A diameter is still considered a chord, but it has to go through the center, and that's my blue segment right there. All right, so chord being my pink segment and diameter being my blue one. All right, so let's jump right into the facts, all right, that we are going to eventually use in our proofs. All right, so the first one deals with central angles and arcs. And if you guys remember from day 2, a central angle, so I'll call that's our center O. A central angle is an angle in a circle where the vertex is the center of the circle. Okay, so angle BOC. And I'm going to add in some other stuff here. I'm going to extend OC to be a diameter there. So that's A, and then I'm going to make D right there. So we got a whole bunch of central angles working right now. Okay, a whole bunch of central angles. Here's what your first theorem says that we can use in a reasons column of a proof. If the central angles are congruent, that means the arcs are congruent. Okay, so angle BOC being congruent to angle COD, if I'm given that angle BOC and angle COD are congruent, that tells me, or this implies, that what's true? They're arcs. So what arc belongs to BOC? BC. And what arc belongs to COD? CD. Because the central angles are equal, the arcs are congruent. Okay? And we can go the opposite way as well and say, all right, if you give me that BC is congruent to arc CD, if two arcs are congruent, that tells me their central angles are congruent. Okay, so one nice little fact maybe we can use in the reasons column one day in our proof, that if the central angles are equal, the arcs are congruent, and vice versa, going backwards. Okay, let's do it with, we can also do this with chords too. Okay, if I know two chords, so let's put a center in there. If I have chord AB right here, and then I draw in chord CD, okay? So if I know that AB, chord AB, is congruent to chord CD, that tells me that the arcs they make are also congruent. So if AB and CD, those chords are equal, so are their arcs that they make. Okay, and most of these theorems that we do, the reverse is always true. So if I know that arc AB is congruent to arc CD, that tells me that AB is congruent to chord CD. Okay, so again, a little quick summary. If the central angles are equal, so are the arcs. If the chords are equal, so are the arcs. Okay, number 3, a little bit different than the first two. If I have a diameter that is perpendicular to a chord, all right? So for instance here, a diameter perpendicular to a chord. So I have AB, diameter AB is perpendicular to chord CE. Okay? If a diameter is perpendicular to a chord, a couple things happen. The diameter bisects the chord. Okay, the diameter bisects the chord, so that would mean CF is congruent to FE. Okay, so if a diameter perpendicular to a chord, it bisects the chord and its arcs. All right, the diameter also bisects the arcs. So arc CA would be congruent to arc AE. Okay? So hopefully that's a big one. Okay, and let me spend some time on this right now just to show you a little bit more. There are times that you may not see a full diameter perpendicular to a chord. Take a look. Let's say I get rid of this part of DB, and you just have that little radius perpendicular to a chord. It still works. All right, it still works because it's still a diameter perpendicular to a chord. Okay, it still works. All right, so if you just see that little portion, the radius instead, it still works. All right, it's just got to be part of a diameter. Okay, got to be part of a diameter. It still bisects the chord. Okay, even let me get rid of AF. You just see that piece right there. As long as it's coming from the center, going through the center, perpendicular to a chord, this theorem still applies. Next one here, number 4, and then we'll start practicing. Chords equidistant. Remember, equidistant, same distance. So if two chords are the same distance from the center of the circle, those chords are congruent. So look at my diagram I have. You see chord DE and you see chord CB. They are both 8 units away from center A. All right, both 8 units away from center A. So they're both the same distance from the center. So that would tell me that segment DE is congruent to segment CB. Those two chords are congruent. Okay? And the reverse can be true as well. This is one we don't usually use too often, but if the chords are congruent, they're the same distance from the center. Okay? All right, so now what I want to do is actually use all these in a... I know you see statements, reasons. Don't freak out. We're not doing actual proofs yet. What I want to do is, from what you're given, tell me what you can conclude. Okay? So they're telling me these two circles are congruent and the arcs are congruent. And the way we can mark arcs congruent on a diagram is the same way you can mark segments congruent. Okay, so I can say PR is congruent to SU just like that. Okay, so a couple things and how to write it properly in the reasons. So if you go back and look at the facts on the previous page, you know that if the arcs are congruent, so are the chords. So we can say PR, segment PR, is congruent to segment SU. Here's the reason. What were you given? What was given? We were given congruent arcs. And what did we write down? Sorry, guys. We were given congruent arcs. What did we write down? That means or implies congruent chords. So that's all I need to write in the reasons column when I want to use that fact. All right. Next up, we also learned in theorem number 1 that if the arcs are congruent, so are the central angles. So angle Q is congruent to angle T. Reason? What was given? That we had congruent arcs. And what did we write down? That means congruent central angles. All right. Now, last thing I want to add in here. Okay, this isn't a theorem we just went over on the previous page, but it's something I can guarantee you're going to use in the circle proofs a ton. All right. Because the two circles were given that they were congruent, I don't want to go back into the packet and go back to all these pages, but if you remember, I want to say day 1 or 2, when two circles are congruent, two circles were congruent if their radii were congruent. Okay, so what are the radii in both circles? You got PQ will be congruent to QR, will be congruent to ST, which will be congruent to TU. Okay, and my reason going to be, I have two congruent circles. You can do the circle symbol if you want. Implies congruent radii. Okay, so there's where we can go there. All right. So what I'd like you to do right now is pause the video and see what you can do with number 2. Given the circles are congruent, and now we can mark this on our diagram. Chord BC is congruent to chord KL. All right, let's see what you can do there. All right, so pause the video. I'll do the same and write in. You should be able to get probably at least 2 of them. Okay, 2 true facts down. So go ahead. Okay, so hopefully you found these 2 statements that the arcs BC and KL were congruent, because if the chords are congruent, that implies the arcs are congruent. Okay, and then number 2 is very similar to number 3 in the previous one, that if 2 circles are congruent, that must mean all 4 radii are congruent. Okay, all right, so now let's put it to some algebra. All right, let's put these theorems to some algebra now. All right. So if we're taking a look at this first diagram here, I want to solve for x. All right, well, this 8, by the way, belongs to the entire chord. Okay, the 8 belongs to the entire chord. So it looks like I have a right triangle. I know the hypotenuse is 5, looking for leg x. It would be nice if I could know that other leg, because then I would do Pythagorean theorem. All right, and I can find that other leg because we have that theorem that said, and I'll just write this one out for you, and then you can do it on your own in the next ones. I have a diameter, and some of you are saying there is no diameter in that diagram, and you're correct. Remember what I said, though. If any part of the diagram is that a diameter is there. Look, I have something coming, a segment coming from the center. So that is part of a diameter. So a diameter, which is perpendicular to a chord, implies that it bisects the chord. All right, so now I can say each side there is 4 and 4, and now I can do Pythagorean theorem to find x. So x squared plus 4 squared equals 5 squared. Okay, and then x equals 3. And I just want to add in here for reasons, explanations. I know it's not one of our theorems, but or circle theorems, but we did use Pythagorean theorem. Okay, so there's one way. All right, we could start using these theorems algebraically. Okay, next up, let's take a look at number 4. All right, again, it's a right triangle. I know a little something about 2 sides. Well, what about that third side that's blank? Is there anything I could write into there? Well, what is that third side called there that's blank? That's a radius. And if I'm in a circle, all radii are congruent. Okay, that's another theorem that we didn't talk about before, but another powerful one. All right, so in a circle, all radii are congruent. Okay, all radii, meaning if one radii is 6, they're all 6. And now I can do a little Pythagorean theorem. So I can say 36 plus 36 equals c squared. 72 equals c squared. Now I get it. The directions say round to the nearest 10th, but I'm sure you know what's about to come out of my mouth right now. That's garbage, especially if we're in honors, right? We're going to do simplest radical form. So go ahead, take your time, find the biggest perfect square that goes in the 72, and here's a hint. It's right above it, 36. All right, so this ends up being 6 square root of 2. All right, one more. Finding, oh, and then we also had Pythagorean theorem. Okay, last one here, number 5. Finding the values of x. All right, well, these are, let me highlight them here. These are chords, right? These are chords, and they're telling me both chords are 7 units from the center. Both chords are 7 units from the center. So on that, one of the last theorems we talked about today was if 2 chords equidistant from the center, what did we go back and look if you need to? If two chords are equidistant from the center, they are congruent. Okay, so I know this full, I'll highlight it even deeper here. This one right here, that chord has to be a length of 6 because the other chord was 6. But now it's asking me either side there of X. Well, that goes back to the theorem, going back up to question number 3, which is, hey, I have a diameter, a part of a diameter that is perpendicular to a chord. So a diameter perpendicular to a chord implies that it bisects the chord. All right, so for this one, I had a chord, I had 6 as the length of the chord. It's getting bisected, so it's going to be 3. Okay, so a couple new theorems here we got to work with, and you'll work with it in your homework. And tomorrow for day 6, we're going to apply these. And then we're going to do them in a proof. All right, so these aren't going anywhere. We're going to have at least another day to work with them. Okay, so see what you can do with pages 719 to 722, and I'll see you at the Google Meet to answer questions. Thanks, everybody.